Hello, everybody. In this lecture, I will continue with the investigation of principal ideal domain and investigation of rings, in particular principal PIDs, and also we will talk about Euclidean domain. Remember, at the end of the last lecture, in previous lectures, what did we do? We define in an integral domain, we define what a prime element is. Remember, an element is prime. Let me remind you, P prime in an integral domain. If P divides A and B, then P either divides A or P divides B. So if one of them is, if this is satisfied, then we call this element as prime in the ring, and P is irreducible. If you write P is equal to A times B, this implies that A is unit, or B is unit. So it cannot be factored out more. And as we know before, in an integral domain, prime elements are irreducible. Prime is irreducible. But in general, irreducible elements are not prime. And example is this ring R. In this ring R, we showed before that 3 is this is an integral domain. This ring, it's a subring of complex numbers. We showed that 3 is irreducible, but it is not a prime number. But in a PID, prime numbers will be irreducible. Irreducible numbers will be prime, and so that this R won't be a principal ideal domain. And here's the corollary that we stated last time. If R is a PID, then every irreducible element of R is prime. So that's our first purpose in this lecture. Now, suppose that P is irreducible in R, and suppose that P divides A and B, then we need to show that in order to show that P is prime, we need to show that either P divides A or P divides B. Okay, we will show one of them. If P divides A times B, then we may write A times B as P times U, by definition. Then, so if P does not divide A, then the greatest common divisor of P and A is 1. Here's the, or is a unit number. And here's the proof, here's the reason for this. So let D be the greatest common divisor of this A and P, so that as we know, we may write D as A times X plus B times Y for some XY in R. So if D is unit, so we need to show that D is unit. If D is unit, then D is associated to 1, so that 1 or D or 1 will be the greatest common divisor of A and B, if D is unit. If D is not unit, we will get a contradiction. Then D divides A. So since D is the greatest common divisor of A and B, D divides A and D divides B. Greatest common divisor divides both of them. And so that we may write A as D times C, and sorry, this is not B, this is P. A and P. P. B is equal to P. Okay. In this case, we may write P is equal to D times E. So therefore, since P is irreducible, so we will show that P irreducible numbers are prime, so that we assume that P is irreducible. P irreducible implies that from here, D or E is unit. One of them is unit. Is unit. And sorry, also we assume that D is not unit. We assume that D is not unit, so that E is unit. E is unit, so that therefore we may write D as P times E inverse from this identity, so that A is equal to, so this equality, D times C, and D is equal to P times, this is C. D is equal to P times E inverse times C, so that P divides A, and this is contradiction. Okay, because we assume that P does not divide A. So this contradiction. Therefore, D is unit. Hence, D is the greatest common divisor of A and P. Or also 1 is the greatest common divisor because D is associated to 1. Greatest common divisor of A and P. So either one. So this is the proof of the greatest common divisor of P and A is 1. And now, therefore, we may write 1 as A times X plus P times Y. So remember, we will show that P either divides A or P does not divide A, so that we will show that P divides B. So remember here, we assume that P divides A times B, and we assume that P does not divide A. Then show here, we need to show that P divides B. So if P does not divide A, then it must divide B. So how do we do this? So from this identity, 1 is equal to AX plus BY. If we multiply both sides by B, B is equal to BAX plus BPY. And B times A is P times UX plus P times BY, because we assume that P divides A times B, so that A times B is P times U. So instead of AB here, or BA, we write P times U, so that when you factor out P, that is UX plus BY, so therefore P divides B, i.e. P is prime. Okay, in a PID, so where did we use that? The question is, here's the question. Where did we use that R is PID, principal ideal domain? That's a good question, and I will not answer that question. I will, you should figure that out. Okay. Next. Okay, here's another definition, another property of rings. This is Euclidean domain. Let me write with capital letters, with different colors. Euclidean domains. This color is nice too. So let me continue with that color. So here is a definition. An integral domain R is called a Euclidean domain. Euclidean domain. If there is a function which will be familiar to you, if there is a function d from, let's use r star. R star is r minus 0 to z integers. This is integers, such that it should satisfy these properties. One is d of r is greater than or equal to 0 for every r in r star. Second property, that if a, b are non-zero, and if a divides b, namely b is a multiple of a, then d of a should be less than or equal to d of b. And the most important property is that if a and b are in R, with b is not 0, then there is a function. Then there are elements q and r in R, such that a is equal to b times q plus r, namely division algorithm, where with, we may write this way, such that either r is equal to 0, or if r is not 0, then dr is less than db. Remember, db is defined. D is defined for non-zero numbers, non-zero elements of R. Okay. So the most basic example is, as always, integers. Example. So let's take R to be the integers, and let's define D from Z star, from non-zero integers, all integers except 0, to Z. Let's define dr as the absolute value of R. So that d of R is greater than 0 for all R, even greater than or equal to 0, but it's greater than 0. Let's write this way. And second, if A divides B and if B is not 0, integer, then we may write B as A times C, so that A and C are smaller, so that absolute value of A is less than or equal to the absolute value of, so that C is greater than or equal to 1. Absolute value of C is greater than or equal to 1, so that absolute value of A is is less than absolute value of A is less than the absolute value of B. So that means D of A is less than or equal to D of B. So that the second property is satisfied. And let's look at the third property. So suppose A and B be integers and B is not 0. By division algorithm that we know, if we divide A by B, there exist integers Q and R such that find integers Q and R such that A is equal to we can Q times B plus R, where 0 is less than or equal to R, less than B. Okay, so either R is 0 here, either R is 0, thus either R is 0 or R is between 0 and B. So that means absolute value of R, which is dr, is less than the absolute value of B, which is d of B. So therefore, thus Z is a Euclidean domain. So that's the basic example. Integers. There is another interesting, important example. So let me state it as a theorem. Let F be a field. For example, real numbers or rational numbers or complex numbers. Then if you look at the ring of polynomials, is a Euclidean domain. So here's a proof. So this f of x is an integral domain, first of all. So R is equal to f of x is an integral domain, we know. Okay. Now let's define D from R star, namely R star is the polynomials, non-zero polynomials, to Z, defined by D of f of x to be the degree of f of x, degree. Okay. So first of all, so D of f of x. So if f of x is not 0, then D of f of x, which is the degree of f of x, is either 0 or bigger. Remember, we defined the degree of 0 polynomial to be minus infinity, or it may not be defined anyway. So otherwise, only the degree of the 0 polynomial is minus infinity. All the others are as non-negative. So that the first condition is satisfied. Second, so let g of x be not non-zero polynomial and f of x divides g of x, suppose, so that we may write g of x as f of x times h of x. since we are in a polynomial or on a field, d of degree of g of x is equal to the degree of f of x plus degree of h of x. But h of x is not 0, otherwise g would be 0. So this is greater than or equal to 0. So that means degree of f of x is less than or equal to the degree of g of x, i.e. plus d of f of x is less than or equal to d of g of x as required. So that's the second property. And in order to show the last property, so given f of x and g of x in f of x with g of x is not 0, again by division algorithm, we proved before by division algorithm. Before, if we divide p by g, then we may write f of x as, so there is a polynomial q, sorry, by division algorithm, there is the polynomials q of x and r of x in f of x in R such that we may write f of x as q of x times g of x plus r of x, where the degree of r is where r of x either is 0 or the degree of r of x is between, oops, this is less than the degree of g of x, and it's greater than or equal to 0. So if r is 0, if r is not 0, so if r is equal to 0, it is one of the conditions, and if r is not 0, so then the degree of r of x, which is the d of r of x, is less than the degree of the second condition satisfied, g of x. So therefore, this f of x is a Euclidean domain. Okay, good. So examples are Qx, namely polynomials with rational coefficients, or polynomials with real coefficients, for example, or polynomial with complex coefficients. Or another important property is that if you take Z2 field, these are all Euclidean domains. Euclidean domains. Nice. Next. And now we will show that. So it is something like this. So if you have rings, let's say a ring as a set like this, rings, let's say some of them are integral domain, some of them are not. Suppose this is the set of integral domains, and inside some integral domains we have some PIDs, and Now we will show that this UFDs are inside, not UFD, sorry, Euclidean domain, are inside PID. Namely, here is the theorem. Every Euclidean domain is a PID, principal ideal domain. Principal ideal domain. Okay, there's the proof. The proof is just like Z, nothing else. Euclidean domain. Euclidean domain means just so namely, how did we show that Z is a PID? What did we remember? How did we show it? So if we take an ideal, if you take the zero ideal, it's generated by zero, and if you take a non-zero, if you have a non-zero ideal, then it contains a positive number, and you look at the least positive number in the ideal, and that generates the ideal, so that every ideal is principal in integers. Now, exactly the same proof works here. So here is the proof. Exactly the same proof. So let R be a Euclidean domain. Euclidean domain with this function, with the function d from R star. Remember, R star is R minus 0 into Z, satisfying this function's properties, satisfying that dr is greater than or equal to 0 for all R in R star. And second, if A divides B and if B is not 0, so if A divides B, then they're not 0, then d of A is less than or equal to d of B, right? And if B is not 0, there exists a Q, R, and R in R such that A is equal to, where A also any element in R, A is equal to Q times B plus R, where either R is equal to 0 or dr is less than dB. That's the condition of Euclidean domain. Now, let's show that this Euclidean domain is a PID. So let's take an ideal. So let I be an ideal in R. If it consists of only zeros, then it is generated by 0. So this is principal ideal. So this is principal. So principal ideal means it is generated by a single element. Now let I is not 0. I is not 0, and choose an element so that the d of you look at d of r's, where r is in R star, and all these are greater than or equal to 0. You look at the smallest one. Choose an element. A in I minus 0, such that this is in R, this is in I. Look at this set. I'm such that this d of A is So choose an element B, such that D of A is greater than or equal to D of B for all A in I minus 0. Okay? Choose the smallest element. Mapping to the smallest integer. So claim I is equal to B. I is generated by this B. And since B is in, so the one of the containment is trivial, since B is in I, then the ideal generated by B, the principal ideal generated by E, so that is R times B, of course, or B times R, since we are in the commutative ring. This is inside I. Now, B is not 0. Oops. Now, let's show the converse. Let B be in I, be arbitrary element. So A be in I, sorry, not B. A be an arbitrary element. So since R is a Euclidean domain, with this part, there exists Q and R in R such that we may write A is equal to Q times B plus R, where either R is equal to 0 or dr is less than dB. So now A is in I, B is in I, so that R is equal to A minus Q times B in I. Now, if R is not 0, then by this assumption, then dr is less than dB. That is so we found another element in I whose D is smaller than D of B. So but this is impossible by the choice of B. So therefore, this first condition must be satisfied. Therefore, R is equal to 0. So since R is equal to 0, A is equal to P times Q times B, and that is inside B. So that every element A of I is inside, every element of I is inside B, this ideal, so that I is a subset of B. So therefore, thus I is equal to this. This is a principal ideal. So that means every ideal is principal. In R is principal. Principal means generated by a single element. This principal. Therefore, R is the Euclidean domain. R is the P principal ideal domain. That's it. Okay. Now about here is I guess let me write a theorem which I will prove in the next lecture because I don't have only 5 minutes to 40 minutes, so that I cannot finish the proof in 5 minutes. So let me state as stated. So the theorem is that let R be a commutative ring. With one, then the followings are equivalent. The followings are equivalent. Namely, one implied the other. The first one is R is a field. This will be a very useful theorem. And second, R of X is a Euclidean domain. Euclidean domain. And 3 is R of X is a principal ideal domain. And proof. So we will prove like this. We will prove that we prove this way, that 1 implies 2, 2 implies 3, 3 implies 1, so any one of them will imply the other. So 1 implies 2, 2i. As we proved before, if we have a field, then R of X is a Euclidean domain, just about theorem. Oh, previous theorem. Let's see, where is it? Euclidean domains are PID before, sorry. This one. If F is a field, then F of X is an Euclidean domain. Is a Euclidean domain, so that this is proved about. Also, every Euclidean domain is PID. Is a PID, so that this 2 implies 3. Now, 3 implies 1. So this is the basic, most important part. And as I said, I will prove this in the next lecture.